We've been talking about chemical equilibrium, and last time we learned how to write, solve, interpret KEQ expressions, how to solve concentrations of substances not indicated if KEQ and the other concentrations were given. Today what we are going to learn how to do is explain and interpret Le Chatelier's principle. You can do this from information provided. You also can do it from experimental data. And next week you'll be doing probably the coolest lab of the year in regard to understanding Le Chatelier's principle. It sounds and looks a lot worse than it is. I'm going to teach it to you in a very simplified fashion. I think you will be very strong in both explaining and interpreting Le Chatelier's principle. In your notes, we already talked about equilibrium involving liquids and solids. We know that when we write KEQ expressions, we only put concentrations of gases and aqueous substances in. We do not put any solids or any liquids in KEQ expressions. So for example here, if you were asked to write the KEQ for this equilibrium reaction, you would not include the calcium carbonate nor the calcium oxide because both of those are solids. So KEQ would be equal to the concentration of carbon dioxide only. In regard to solubility equilibrium, I'll gladly come back to this next week for those of you who want to learn it. It is strictly optional. It's good practice for AP or college chem. Not something you'll be assessed on, so I'm going to skip it for today. We can come back to it next week. And where we're picking up is right here with Le Chatelier's principle. There are several factors that can alter chemical equilibrium in that either the rate of the forward or the rate of the reverse reaction will be favored. These factors are stresses, and they are different from the factors that affect kinetics. In the kinetics chapter, we talked about how concentration, surface area, temperature, what the reactants are, and catalysts can affect rates of reactions. In equilibrium, it's a little bit different. The factors or stresses that can alter equilibrium such that either the forward or reverse reaction is favored. These factors include concentration, temperature, and pressure or volume, so not surface area. Be careful with the two chapters being assessed at the same time. It's easy to confuse concepts. So in chemical equilibrium, the factors we're going to be looking at include concentration, temperature, and pressure or volume. And we'll talk about all of these. Le Chatelier's principle says that if you do something to disturb or perturb a system that is at equilibrium, the system will respond in such a way that at least partially undoes what you have just done. It's going to do something to at least partially relieve the stress. So what's going to happen here is you're going to have an equilibrium system where the rate of the forward and reverse reactions are equal, and you're going to perturb equilibrium. And what you want to do is figure out in which way equilibrium will shift, understand why equilibrium shifts in that manner, and then also look at the outcomes, whether products or reactants will increase in amount. Now when you look at a textbook or just go online and Google this, you'll come up with some explanation that will be very difficult to interpret. So we're going to use a much simpler system to get it started with the hope that you will understand it and master the concept with ease. In your notes, I have a whole table for you to fill out, and that's shown on the screen here. Before we fill all of this out, I do want to explain a couple of key things. When you increase concentration or temperature, what you're going to see is that equilibrium shifts away from that entity. And when we walk through the examples, you'll see exactly what we mean there. Increase, equilibrium shifts away from that entity. When you decrease concentration or temperature, these are two factors or stresses that can affect equilibrium. You'll see that equilibrium shifts toward that entity. Now be careful, we're going to increase or decrease concentration or temperature, and we need to predict equilibrium shifts. Now equilibrium will shift either in the forward direction, where you'll generate product and use up reactant, or equilibrium will shift in the reverse direction, where product concentration will decrease and reactant concentration will increase. So equilibrium will shift either in the forward or reverse direction. The away or toward will help you with your interpretation, but don't write equilibrium shifts away. That's very unclear. So equilibrium will either shift in the forward or right direction, or the reverse or left direction. So for example, one stress we can look at is concentration. Another stress that we can look at is temperature, capital T for temperature. If we increase the concentration of A, the way that I like to approach this is I look at my balanced chemical equation showing equilibrium, a reversible reaction with equal rates. If I increase A, I'm adding more A to the system. A's increasing. Well, if I increase, I can see that equilibrium will shift away from that entity. If I'm shifting away from A is on the left, I've got to have equilibrium shift in the forward direction. So when I increase the concentration of A, equilibrium will shift in the forward direction to use the added A. Anytime equilibrium shifts in the forward direction, you'll see products being generated, reactants being utilized. So initially, I increased A, that's what I did, but with the forward shift in equilibrium, reactants will be consumed, so they will decrease, products will be made, so they will increase. You'll see this decrease is not as much as the initial increase because you only partially undo what you have done. Increase the concentration of a reactant, equilibrium shifts in the forward direction to use that substance, in this case A, that you added. With a forward shift in equilibrium, product concentration will increase, reactant concentration will decrease, although this one initially was increased Upon the shift, it decreases. Does that make sense? Let's take a look at another. If I decrease B, I go back to my equation for the analysis. And again, your equation will be provided to you. So now I'm going to decrease the concentration of B. I'm going to pull B out of the system, probably by reacting it with something. If I decrease, I have to have equilibrium shift toward that entity in an effort to replace it. So now equilibrium is going to shift in the reverse direction to replace the removed B. So initially I removed B, but with the reverse shift in equilibrium, these two, A and B, get generated, so their amounts will increase. Shifting in the reverse direction causes these substances to be consumed, so their concentrations will decrease. So changes in equilibrium can occur with a change in concentration. It won't alter the value of KEQ, so KEQ will remain constant, but equilibrium will shift either in the forward or reverse direction in an effort to at least partially undo what the stress has done. Let's look at this one. We've got an increase in the concentration of C. If I increase concentration of C, I'm going to feed it right here. And now equilibrium will shift in which direction? Away from it or toward it if you increase? Away. C is on the right side. I have to shift away from it, so equilibrium shifts in the reversed or left direction. So in this case, equilibrium shifts in the reverse manner, and that is to use the added C. So again, anytime you add something, you will shift away from it so that you are using it. Anytime you remove something, you'll shift toward it in an effort to replace it. So initially we increase C. With the reverse shift in equilibrium, what happens to the concentration of C and D? They're going to decrease. And what will I'm going to stay with my color scheme in case you were doing it as well. I don't want that to be confusing. So initially I increased C. With the reverse shift in equilibrium, C and D will decrease and A and B will get generated, so they will increase. I don't like to memorize what happens. I like to interpret. I think it's much, much easier. And if you can understand these shifts due to changes in concentration, you will find Le Chatelier's principle relatively straightforward and very manageable. Temperature is another factor that affects not only equilibrium in regard to a shift, but temperature is the only stress or factor that alters the value of KEQ. So there are three stresses on equilibrium: concentration, temperature, and pressure. but only temperature alters the value of KEQ. When you go into advanced chemistry, you learn a lot more about it, but for our purposes, temperature is the only factor that alters the value of KEQ. When we work these particular equilibrium reactions in regard to temperature alterations, we're going to feed or remove temperature at that energy term. Now, looking at this generic equation I gave you here, is that endo or exothermic? Endo. You are absorbing energy, so delta H would be positive or negative? Positive. So instead of writing this, I could have left that energy out and said, oh, delta H is equal to positive 36.2 kilojoules. And you would know to put that energy term on the left side because delta H is positive, indicative of an endothermic reaction, something that you mastered in the thermo chapter. In regard to the interpretation with temperature, it is grossly similar to what you see in regard to concentration. So if I increase temperature, I'm going to feed in right here. Anytime I increase, I shift away from that entity. Energy's on the left. So with an increase in temperature, equilibrium shifts in the forward direction to use the added heat. And with a forward shift in equilibrium, products get made, reactants get consumed. You don't have the up, down, down, up situation because you didn't alter the concentration. So let's see if you're understanding. If I decrease temperature, I'm going to put the decrease right here. In which direction will equilibrium shift with a decrease in temperature? Reverse. Same reasoning that we saw here to replace the lost or removed heat. With a reverse shift in equilibrium, what happens to concentration of A and B? They go up. So whatever you point to goes up, whatever you point away from goes down. And that is Le Chatelier's principle, showing changes in concentration and temperature on equilibrium. And again, temperature is the only factor that alters the value of KEQ. So using this very, very simple analogy, we now can go through and analyze equilibrium reactions to figure out whether equilibrium shifts in the forward or reverse direction based on the stress that you apply to the system. Now in your notes, this is all written out in excruciating detail. Again, if you increase reactant concentration, equilibrium shifts in the forward direction, so that particular added reactant can be utilized. Specify which reactant was added. Anytime you shift in the forward direction, reactant concentration will decrease, product concentration will increase. Note that the value of KEQ does not change in regard to concentration. It only, there should be a comma here, only temperature alters the value of KEQ. And again, everything that we talked about is listed. Looking at this first example, let's work it together. It says determine whether equilibrium shifts in the forward or reverse direction. Indicate whether the concentration of reactants or products increases. Explain your reasoning. Let's take a look. First example. It says determine whether the forward or reverse reaction is favored. Indicate whether the concentration of reactants or products increases. Explain. Equilibrium reaction showing the synthesis of ammonia from nitrogen gas and hydrogen gas. If I increase the concentration of nitrogen gas, that's on the left, equilibrium would shift away from it, which would be in the forward or reverse direction. Right, so in this case, the forward reaction is favored because equilibrium shifts forward to use the nitrogen gas added. Concentration of products increases with a forward equilibrium shift as products get generated, made, produced, whatever. In the next one, we want to decrease the concentration of hydrogen gas. Again, feed it in. When you decrease, do you shift away from the entity or toward it? Toward it. So equilibrium shifts in the reverse direction. So here, the reverse reaction is favored because equilibrium shifts to the left to replace H2 removed. So now if you shift in the reverse direction, which concentration increases, reactant or product? Yes. So reactant concentration increases with a reverse equilibrium shift as reactants get generated. If we decrease the concentration of ammonia, NH3, which reaction is favored, forward or reverse? Forward. Why? Because we are going to shift in the forward. Equilibrium will shift in the forward direction in an effort to replace the ammonia lost. So if we decrease ammonia, the forward reaction is favored because equilibrium shifts forward to replace the ammonia that's removed. And with a forward shift, what concentration increases? Product. So product concentration increases with a forward equilibrium shift as products get generated. So it looks really hard, but if you work it very systematically, I think you'll be very successful with it. And we're going to continue to work a bunch of examples. Now, temperature we're treating very similarly to concentration. It's a little bit tricky if you look it up online or look in a textbook in regard to the wording. I'll show it to you, but it can be very misleading. So I really like to just work temperature into that energy term and interpret it from there. It says if temperature is increased in a system, equilibrium shifts in a manner that favors heat absorption, which is endothermic, and that's to utilize heat added. If you decrease temperature, equilibrium shifts in a manner that favors the exothermic direction in a manner so that you replenish or replace heat that you have lost. Again, temperature is the only stress that affects the value of KEQ. Let's take a look. Determine whether equilibrium shifts in the forward or reverse direction. Indicate whether the concentration of reactants or products increases due to that equilibrium shift. So shown here is another example. We've got nitrogen dioxide and dinitrogen tetroxide plus energy. So this is exo. Now instead of telling it to you this way, I could have said delta H is negative, and you would plug in the delta H value. Actually, you'd plug in the absolute value of the delta H right here, because when you're writing a chemical reaction, you don't put negatives into it. You're always adding. That's a little bit unusual. I'll show you what I mean in the next section. So in this one, if we increase concentration of dinitrogen tetroxide, in which direction will equilibrium shift? Reverse. So equilibrium shifts in the reverse direction to use N2O4 added, resulting in an increase in concentration of reactant. So the concentration of nitrogen dioxide will increase due to the reverse shift in equilibrium. What if you decrease concentration of nitrogen dioxide? In which direction will equilibrium shift? Reverse. So equilibrium shifts in the reverse direction. Why? To replace NO2 removed, resulting in an increase in reactant concentration, although it doesn't really increase overall. Here's the temperature piece. If I decrease the temperature, equilibrium will shift in which direction? Be careful here. I'm decreasing temperature. Temperature's on the right. When I decrease, do I shift toward it or away? Toward. Decrease toward. Increase away. Vowel, vowel. Increase away. When I decrease temperature, equilibrium shifts in the forward direction to replace the lost heat, resulting in an increase in product concentration. So understand that that product concentration increases due to the forward equilibrium shift. So if they ask you why the product concentration increases, that's due to the fact that equilibrium shifted in the forward direction in an effort to replace the heat that was removed. So that's concentration and temperature, and those are usually pretty straightforward. In regard to the stresses or factors that affect chemical equilibrium, we've got 3 or 3.5, if you will. So those stresses include concentration, temperature, and you'll see pressure and volume. Only the temperature alters the value of KEQ. Think back to the gas chapter. What is the relationship between pressure and volume? Opposite. They're inversely related. With bubble wrap, for example, you're playing with bubble wrap and you're pushing and squeezing. The volume decreases so much so that the pressure increases to a point at which the bubble pops. Pressure and volume are inversely related. So what you're going to see is if you increase the pressure of a system at equilibrium, equilibrium will shift to the side of the reaction that has the smaller volume of gas due to the inverse relationship between pressure and volume. If you decrease pressure, equilibrium shifts in a manner that favors the larger volume of gases. That volume of gases is determined from the stoichiometric coefficients. We've talked about stoichiometric coefficients representing moles of substance. We know that stoichiometric coefficients also represents volume of gaseous substance. We've done it in regard to volume ratios. So in your notes, as I indicated, when you increase pressure, equilibrium shifts to the side that favors the smaller volume of gaseous particles. That's determined from the stoichiometric coefficients, and the reason is based on the inverse relationship between pressure and volume, which is known as Boyle's law. If you decrease pressure of a system, equilibrium shifts to the side that has the larger volume of gaseous particles. However, if you alter the pressure and the volume of gaseous particles in reactants and products is the same, the alteration in pressure has no effect on equilibrium. That no effect is shown here. In this equilibrium reaction, we have 1 plus 1 is 2 mils or 2 liters, whatever unit of volume you want to use, of gaseous reactant. We have 2 mils of gaseous product. Regardless of what you do to the pressure, whether you increase or decrease it for this system, there will be no effect on equilibrium because the volume of gaseous reactant and product is the same. They're both 2 mils. In contrast, if you look at this example here, you've got ammonia and you've got hydrogen chloride gas reacting to form solid ammonium chloride. On the left side, we have 1 plus 1 is 2 mils of gaseous reactant. We don't have any gaseous product on the right. If you increase pressure, equilibrium shifts to the side with the smaller volume of gas. So equilibrium would shift forward. So you would have a forward arrow here. And that is because the volume of gaseous product, which in this case is 0 mils, is less than the volume of gaseous reactant, which in this case is 2 mils. And pressure and volume are inversely related according to Boyle's law. Okay? So, if you increase pressure, equilibrium shifts to the side with the smaller volume of gases because of Boyle's law. If you decrease pressure, equilibrium shifts to the larger volume. So whichever side of the reaction has the larger volume is the direction of equilibrium shifting. So let's use that, and now let's get pressure, concentration, and temperature. So in this second example, there are a few things to consider. We have an equilibrium reaction. I'm giving you delta H. Exothermic is correct. So you can either write plus 6.2 kilojoules here, because once you add it to the right side, you know it's exothermic. Or you can just write plus energy, capital E for energy. I'd feed it in this way because that's going to help you with your temperature interpretation. If pressure is decreased, equilibrium will shift to the side with the larger volume or greater volume. So let's take a look. We've got all gases. 4 plus 5, 9 mils of gaseous reactant. 4 plus 6 is 10 mils of gaseous product. If pressure is decreased, equilibrium will shift in the forward direction because the volume of gaseous product, which is 10 mils, is greater than the volume of gaseous reactant, which is 9 mils. And we know that pressure and volume are inversely related. What if I decrease concentration of nitrogen monoxide? Equilibrium will shift in the forward direction to replace NO removed. And again, when you shift in the forward direction, product concentration will increase, reactant concentration will decrease. What about this one? The temperature of the system is increased. Increase, equilibrium will shift to the left. Increase, shift away, it's on the right, you'll shift to the left to use the heat added. That will cause an increase in reactant concentration and a decrease in product concentration. In regard to Le Chatelier's principle, you want to consider stresses of concentration, temperature, and pressure. One thing I do want to mention before you do the last practice problem is in this first example, this has come up in some of my advanced classes repeatedly, and it didn't stick, and I'm not sure why, so I want to make one thing clear. In this equation shown here, if I increased or decreased the amount of ammonium chloride, we would not see an effect on equilibrium. Do you put solids in KEQ expressions? No. So regardless of what you do to the solid, there'll be no effect on equilibrium. Taking a look at this third example here, you want to do it together or alone? Alone? Let's take 2 minutes to give it a shot, and then we'll go through it.
The question before that, if it was endothermic, would it be forward instead of reverse?
Yes. And always put the energy term in so you can make the proper interpretation. That's a good strategy. Yes, yes. How we doing? Ready? Looks like I went a little crazy with decreased in this question. Did we do it right? You got it? Your explanations are clear?
Why is the last one reverse?
This is an endothermic reaction, so we put energy here. If we decrease temperature, we have to shift toward it. Energy's on the left side, so we shift in the reverse or leftward direction to replace the heat loss.
I thought it was like
No, because it's positive.
Yeah.
Careful, careful. Also, in this regard, if the temperature of the system were decreased, why would concentration of reactants increase? Because with the reverse shift, the reactants would get generated, right? I'm just trying to think of any question I might have asked you. Okay, last couple mentions. This link takes you to a YouTube video on Le Chateliers principle. It's about 7 minutes. You're welcome to watch it on the Chromebooks if you wish. It is a little advanced, but there are some simplistic concepts in there. In the event you were going to miss the lab next week due to testing, I would definitely watch this because this is a link to the reaction we are running. On your quiz, you will be assessed on the following. I will give you an equilibrium reaction. You will write the KEQ expression. You'll calculate it. You'll interpret it. You'll calculate a concentration when given KEQ and other concentrations, and then finally you'll have some questions on Le Chatelier's principle, grossly similar to what I've shown you today. The classwork that you want to complete is as follows. We are omitting 8 through 9 through 12. You already did 1 through 8. So we're omitting 9 through 12. Although some of you, I think we should go over 10 through 12. I think it would be a good setup for next year. Questions on anything in regard to Le Chatelier's principle? It is a very challenging concept, but if you work it simplistically, I think it will be very easy for you. Your lab will be very good, not only because it's fun and quite dangerous, but also it really illustrates Le Chatelier's principle in regard to color change. So I think it will really help nail this concept down. You want to understand what Le Chatelier's principle is, the 3 factors that are stresses, and how to predict stresses in equilibrium based on stressing or perturbing the system in some way.